Hello everyone, welcome back to another session for thermodynamics subject. In this session we are going to continue our discussion about the enthalpy, energy and also the specific heat of different substances. In previous session we had discussed about the enthalpy, internal energy and also specific heats of different gases, especially we discussed about the ideal gases, and we have seen how we can use these different properties to find each one of the other thermodynamic properties for that substances in different processes. In this session, we will continue and we will introduce specific heat for incompressible substances like solids and liquids. These incompressible substances actually are substances which their specific volume or density is constant, which may you already know about that, like different kind of solid like iron, which its volume doesn't change with uh, change in the pressure, with change in the temperature and so on. However, it may change, but it is not comparable with the change uh, in the volume of the gases. We change in the temperature or pressure. So usually we call these substances as incompressible uh, substances, and which include solid and liquid. For these substances, we don't have CV and CP or a specific volume in a constant volume process or a specific heat or a specific heat in constant pressure process. Generally, we have only a specific heat for these substances, and we show that by C, and we call that a specific heat for the different types of different substances, different solid and liquid substances actually. So we don't have Cv and Cp for solid or liquid substances, and we have only uh, C. And why we call these incompressible substances, as I said, because their specific volume during a process remains constant, and it doesn't change during a process. This is, generally what we may deal with is not about solid substances, and what is more important in thermodynamics is about different incompressible liquids, which we will discuss about them uh, further. Let's see how is the internal energy changes for these kind of substances during a process. If you remember, we had this equation du equal to Cv dt for gases. If we want to write this equation for the liquid or substances, we don't have C and we just write like this: du equal to C as a function of T dt. In other words, like uh, like compressible gases or like gases for liquid and solid, specific heat is a function of the temperature for that substance, and du is function of the specific heat of that substance and change in the temperature of that substance. And also remember, if you remember, we had this equation for the get different gases, and also for incompressible substances we have similar equation, but if you notice here again we have only C as a function of the specific heat at temperature of T. U2 minus U1 equal to integrate of C as a function of T, dt in terms of kilojoule per kilogram. And also the other equation as well, like this which we had for the different gases, delta U is approximately equal to C average T2 minus T1. If you remember, this was like this. But here, for solid and liquid, we don't have Cv or Cp, we have only C. Again, we can use that equation, but this time we have only C, not Cv or Cp. So you can see those equations which we had for the different gases can be used as well for the solid or liquid and incompressible material substances. But this time we don't have Cv and Cp, and we have always C or a specific heat of that substance. And the enthalpy changes of these kind of substances can be also calculated according to what we know about the uh, gases, and we have what we have learned about them. Generally, you know that enthalpy or H is equal to U plus PV, U internal energy, P pressure, and V volume of that substance or a specific volume of the substance. If we differentiate both sides of this equation, it will be dH equal to du plus V dP plus PdV. This part is uh, derivation of this PV, derivation of the multiplication. If you know from mathematics, PV first we write the derivative of the uh, first term times uh, second term, then plus uh, first term times derivative of the second term. And this is from mathematics, so dPV will be equal to V dP plus P dV. This is from mathematics, and just you may recall that. And as you know, here for substance for these incompressible substances, we don't have change in the volume of the substance during a process. Then dV will be equal to 0, and this term will be 0. Then dH will be equal to du plus V dP. This is the equation which we have, and if we write in terms of delta, delta H equal to delta U plus V delta P, or generally C average delta T delta U, what we found here. We can write like this: delta H, we write delta U as a C average delta T, C average delta T instead of delta U plus V delta P. This is the change in the enthalpy of these incompressible substances during a process. And as we discussed earlier, it doesn't relate to the process. Process can be constant volume or constant pressure and so on. And as I said, generally we usually consider the different liquid in thermodynamic at solids especially. And for solids, the V delta P also is insignificant. Generally, the volume of the pressure of the substances also doesn't change. In other words, pressure in these substances, different solids, are insignificant and is very small. So we can just ignore this term as well. Then we have only this delta H equal to C average delta T, which is identical to delta U. In other words, change in the enthalpy is equal to change in the internal energy of the solid substances, and it is equal to the average specific heat of that substance time change in the temperature of that substance during a process. This is for solid substances. In liquids, we have two special cases. First, in constant pressure processes, which we have in heaters, different types of heaters we have already seen in previous example, like electrical heater and so on, which may a heater mm, contain a liquid then we may have a constant pressure process in that heater. For that heater, delta P or pressure will be 0, then delta H or delta U, similar to the solid, will be equal to uh, each other, or delta H and delta U are identical. Changing enthalpy is equal to change in the internal energy, equal to the change in the temperature of that substance, time specific heat of that substance, or average specific heat of that substance uh, between temperature T1 and T2. And the other special case is the constant temperature process. And as you know, we have this type of process in different pumps. In pumps, generally temperature of the liquid, here it's about the liquid. Liquid in pump generally uh, just experience in an increase in the pressure, and the temperature of the liquid generally should be constant. So delta T is equal to 0. For this case, delta H will be only equal to delta P, like what we can see here. For in this case, we have delta H, or a change in the enthalpy of that the liquid during the constant temperature process is equal to change in the pressure times specific volume. This is like what we have in different pumps. These two devices actually, or components, are important in thermodynamics because we have them in different uh, uh, equipment and different application, thermodynamic application we have for pumps and heaters. And as you can see, for when we have a liquid in a pump, delta T is equal to 0, and the process in the pump is a constant temperature process. So the change in the enthalpy is the equal to change in the pressure times change in the specific change in the pressure times specific volume of the liquid. And generally, we have this equation actually to find the enthalpy of a compressed liquid. If you remember, in previous chapters we had discussed about different state of liquids, especially we discussed about the water, and we introduced the compressed liquid phase of the water. This compressed liquid phase can be for the other liquids as well. To find enthalpy for this kind of substances, we need to use this equation. Enthalpy of a liquid with pressure of P and temperature of T is equal to the enthalpy of that substance, or for saturated in saturated liquid state at temperature T, plus specific volume, saturated specific volume at temperature T, times the pressure which that substance is, and minus saturation pressure of that substance at temperature T. General equation, we will see in an example how to use this equation. This is general equation to find the enthalpy of compressed liquid. Then we can put in this equation and calculate delta H for that liquid actually. So this is the general equation to find enthalpy of a compressed liquid. Usually, when you remember from previous chapter, we have compressed liquid when the pressure of the uh, substance, or pressure of the liquid is higher than saturated uh, pressure, saturated liquid pressure actually, or uh, uh, P at mm, when temperature and pressure and temperature are saturated pressure and saturated temperature actually. However, this equation, as you can see, has different components, and it is not that much easy to calculate that. And we have a simplified form of this equation, which is this one, enthalpy of a liquid or a compressed liquid actually at pressure P and temperature T is approximately equal to saturated saturated enthalpy of saturated liquid enthalpy at temperature T, or HF at temperature T. This is simplified form of this equation, which you have already seen how we can find HF, or enthalpy as saturated liquid, from the different tables. So if you find this for a liquid from table, for example, for water, you can just refer to table A5 or A4, I think, if I remember correctly. Then you can find this HF for uh, water at that temperature. This is the simplified form of this. However, because we ignored this part of this equation, usually we have some error to find enthalpy by this equation. We will see in an example how we can use these two equations to find enthalpy for a compressed liquid. Here we have an example to see how we can use those equations actually, which I show you, to calculate or to find the enthalpy of compressed liquid. In this example, we are going to determine the enthalpy of liquid water at 100 degrees Celsius and pressure at 15 megapascal. We need to do this by three different methods: by using compressed liquid tables, which you have already seen in previous chapter. It is table A7, I think we will see. And in part B, we need to find this enthalpy for water with these properties by approximating uh, it as a saturated liquid, in other words, HF. And in part C, we need to use this equation for 38, which means this equation, which I already introduced you, to find enthalpy of compressed liquid. First of all, why we call this compressed liquid? As I said, the for a compressed liquid, the pressure of the liquid is much higher than the saturated pressure of that uh, liquid. So for water at 100 degrees Celsius, saturation pressure is 101.42 kilopascal. How we know that? If you We can get this information from table A4. If you go to the table A4, you will find saturation pressure for water with this temperature. This will be this much. But pressure which we have here is 15 megapascal, or 15,000 uh, kilopascal, which is much higher than 101.42 kilopascal. In other words, here we have a compressed liquid. So the water is compressed liquid. In part A, we need to find enthalpy by table. The table which we can find properties, different properties for compressed liquid, for compressed water actually, is table A7, which we have here. If you notice in this table, we have different properties like a specific volume, internal energy, enthalpy, entropy for compressed liquid water in different temperatures and different pressure. The pressure which we have here is 15 megapascal, and temperature is 100 degrees Celsius. Then let's see how much is the enthalpy here for 130.39. And this is the most accurate value which we can find for the specific enthalpy for compressed water, or water in compressed liquid phase or state. This is exact value. In part B, we are going to approximate these as a saturated liquid. From this, if you go to table A4, you will find HF, or enthalpy, saturated enthalpy of water at this temperature, and we uh, just find this value as enthalpy for compressed liquid as a approximation, which is 419.70 kilojoule per kilogram. If you compare these two values, you can see here with this approximation we have 2.6% error uh, to for enthalpy, which we can find by this method. And in third method, we need to use this equation. In this equation, we need to find the enthalpy at this pressure and this temperature, 15 megapascal, 100 degrees Celsius. We need to use this equation, saturated uh, enthalpy at saturated pressure, this one, and specific volume from the table. Again, if you go to table uh, A4, this one as well, table A4, you can find these values, and P minus P saturated. P, which we have here, is 15 megapascal or 15,000 kilopascal, minus saturated pressure, which is 101.42, again from table A4. And if we substitute here, then we use this unity conversion ratio, then we will find this much as enthalpy for water as a compressed liquid with these properties, which is 434.7 0.07. And if we compare these three to each other, you can see here the error with this method by this equation will give us more accurate value for enthalpy. As I said, this is the most accurate. The exact value is one. These two are two approximation. The first one, error for the first one as a saturated liquid is 2.6% error. And if we use this equation, we will have only 1%. But generally, in industry and in real application, we don't need this much of accuracy. And if we just use this method with this much of error, it is acceptable generally. So we don't need to go through this calculation, and generally we can just use this approximation to find H at P and T as a compressed liquid. So you can see how this approximation can help us uh, to do not to let us do not go through these calculations. We have an example here which is about cooling of an iron block by water. We have a tank which is adiabatic or insulated tank actually. It means we don't have any heat or energy transfer between this tank and the surrounding. And so we have water inside it. It is filled with water. We will drop or we will fall a piece of iron into this water. The mass of this iron block is 50 kilogram and its temperature is 80 degrees Celsius. And temperature of the water is 25 degrees Celsius, and the volume of the water is 0.5 meter cubed. So we drop 50 kilogram of iron, which its temperature is 80 degrees Celsius, higher than temperature of the water, which is 25 degrees Celsius. We know how much is the volume of the water and how much is the mass of the iron block. Then what we need to determine is temperature when thermal equilibrium is reached. Thermal equilibrium means both temperature of iron and water will be identical. So let's see how we can find this temperature. If we uh, generally if we do something like this, if we drop this iron block which its temperature is higher to water, uh, to a tank containing water with lower temperature, the thermal energy from iron which has higher thermal energy will transfer to the water which has lower temperature. Generally, temperature or thermal energy or heat will transfer from the substance in higher temperature to substance with lower temperature. So thermal energy will uh, transfer from iron to water until their temperature will be identical. In other words, temperature will be less than 80 degrees Celsius and higher 25 degrees Celsius. Let's see how much is the identical temperature for both of these substances. First, let's see what are our assumptions. Assumption number one is both water and iron block are incompressible substances. As you know, we can have this assumption. Assumption number two, constant specific heat at room temperature can be used for water and iron, which we can have this assumption as well, according to what I told you about incompressible substances. The system is stationary. We can have also this assumption, no movement, no elevation. So kinetic potential energy or delta Ke, delta Pe will be 0. Then the change in the energy of the system is only due to the change in the internal energy of the system here. And also there are no electrical shaft or other form of the work involved in this system. And the system also is well insulated and there is no heat transfer for the system. First, let's see what should be our system or what can be our system here. We select the entire content of the tank, which includes water and iron, as our system. So this is our system, which the blue area actually, blue space, which includes the water and iron. In this system which we have selected, we don't have any mass transfer between the system which we have and surrounding. In other words, what we have here is a closed system which doesn't have any mass transfer with the surrounding. No mass transfer through boundary of our system. And also the volume is constant, so we have a constant volume process here and we don't have any boundary work as the energy balance for our system or E in minus E out will equal to delta I. This is the general form of energy balance for closed systems. E in E out for our system is equal to 0 because we don't have any heat to the system or thermal energy. We don't have any work on the system. We don't have any work by the system, no boundary work. So E in minus E out, both of them are 0. So this will be 0. And delta E of the system is also equal to change in the internal energy. So also delta U of our system is equal to 0. In other words, U2 minus U1 is 0. But what are U2 and U1 for our system? The total energy U is an extensive property, and in other words, U is can express as the sum of internal energies of parts of the system. Parts of the system means iron block and water. So delta U of the system can be defined like this. Delta U of the system is equal to delta U of iron plus delta U of water, or change in the internal energy of the system is equal to change in the internal energy of the iron plus change in the internal energy of the water. Delta U of the system is equal to mc T2 minus T1. You know this equation from previous slides, which we had delta U or U2 minus U1 was MC delta T, if you remember. Then here we have delta U of the system, like this capital U. What we have here, MC T2 minus T1 is equal to delta U of system for iron. And we have also MC T2 minus T1 for water. In other words, in this part of the equation, M is M of iron, C is the specific mass of iron, C is specific heat of iron here, and T2 minus T1. T2 is final temperature, we don't know how much is it, and T1 is initial temperature of iron, which was 80 degrees Celsius. Same here, this term is M is mass of the water, C is a specific heat of the water. We don't know how much is T2, but T1 for water is 25 degrees Celsius. The mass of iron was given according to the question instruction is 50 kilograms. So we have mass of the iron. How about the mass of the water? To find mass of the water, we need to use the table. According to table A4 or other table which we have for water, at room temperature or 25 degrees Celsius temperature, the specific volume is equal to 0.001 meter cubed per kilogram. Then we can find mass of the water by this equation, V or volume of the water divided by the specific volume of the water. We have volume of the water, it was given 0.5 meter cube, and we have also a specific volume of the water which the result of this equation will be 500 kilogram. So we have 50 kilogram iron and 500 kilogram water. So we have also mass of the water. How about a specific heat of the iron and water? To find it, we need to go to the table A3. In table A3, we have for water a specific heat in temperature 25 degrees Celsius is for, this is a specific heat, is this is temperature. So for water with this temperature, specific heat is 4.8 kilojoule per kilogram Kelvin. And for iron, which we can find in the table A3b, we find iron, and the specific heat here is 0.45 kilojoule per kilogram Kelvin. So we can find the specific heat for water and for iron from the table. Then if we substitute in that equation, this equation, we will have this is mass of the iron, specific heat of iron, T2, the equilibrium temperature, we don't know how much is it, and initial temperature of the iron. Again, mass of water, specific heat of water, T2 we don't know, and initial temperature of water equal to 0. If we solve this equation, in this equation, the only unknown is T2, one equation, one unknown. If we can solve this equation, we will find this much. T2 equal to 25.6 degrees Celsius. So you can see here the final temperature of this system, which includes or contains water, 500 kilogram of water and 50 kilogram of the iron, will be 25.6 degrees Celsius. You can see here temperature of the iron is reduced significantly from 80 degrees Celsius to 25 degrees Celsius, 25.6 degrees Celsius, and temperature of water is increased just in a small value, zero point 0.6 degrees Celsius. Initial temperature is 25 degrees Celsius. Its temperature is increased because equilibrium temperature is for whole system. So temperature of iron and water at the equilibrium state will be 25.6 degrees Celsius. Temperature of water is only increased by zero point 0.6 degrees Celsius, and this is due to the huge or very huge value or large value for the specific heat of the water. If you compare the specific heat for water and iron, you can see that as well, which is about more than 8 times or 9 times higher than the specific heat of iron. It means we need more energy, or here thermal energy, to change or increase temperature of uh, water compared to the iron. This is also what we can see in this example, and we found the answer, which is the equilibrium temperature will be 25.6 degrees Celsius. In this example, we are going to see how we can use that specific heat concept actually for solid material to understand how this specific heat is effective on the heating of aluminum rods in a furnace. In other words, this is a general uh, industrial operation actually. We are going to increase temperature of aluminum rods in a furnace, which we can see in different industries, especially which they are encounter such equipment. We have a long cylindrical aluminum rods, which its density is 2,700 kilogram per meter cubed, and its specific heat or specific heat with constant pressure, however, it can be seen only, is equal to 0.973 kilojoule per kilogram Kelvin. Uh, and 5 centimeter, and its diameter is 5 centimeter. It is heat treated from 20 degrees Celsius to an average temperature of 400 degrees Celsius. So initially, when this rods is going to this oven, its temperature is 20 degrees Celsius, and the final temperature will be 400 uh, degree Celsius. And it is drawing by drawing them at a velocity of 8 meter per minute. So the speed of this rod, the movement of this rod inside the oven is 8 meter per minute. We need to determine the rate of heat transfer, or Q dot, to the rod. If we select the rod as our system, we can write Q dot into our system. We need to find this for our system. So let's see what can be or should be our assumptions. First, the thermal properties of the rods are constant during this process. Heat treatment. Two, there are no changes in kinetic and potential energies. We use this assumption. However, we have movement here for our system, but later we will see which we can deal with the example as a constant, as a stationary system actually. And rods, not balls. The rods are at a uniform temperature when they leave the oven. In other words, the temperature, we assume that temperature of the rods at the exit of the oven output of the oven is identical in each place of that rod. This is our assumption. Then this aluminum rod can be is moving with constant speed, which is 8 meter per minute. And if you noticed, we can imagine that we have a 8 meter long rods inside the oven as a stationary a fixed rod in the oven. In other words, we can imagine we have a fixed rods in an oven for 1 minute. Then we take 8-meter long section of these roads as our system. The energy balance for this closed system, because if we select the roads as our system, we don't have any mass transfer from the roads to surrounding, from our system to surrounding, or from surrounding to the system. So the mass transfer for our system is zero. So we have a closed system. Then we write this energy balance equation for our system, our roads. E in minus E out equal to delta E of the system. We don't have any E out for our system, but we have E in or Q in, which is the thermal energy transferred from the oven to our system, which is road. Q in will be equal to delta U, or change in the internal energy of the system. As we said, we have delta KE, delta PE equal to 0 according to our assumptions, which we can deal with this one as a fixed or a stationary section of the rows for 1 minute. Then this delta U road also can be written like this: M, or mass of the road, times uh, specific internal energy of aluminum rods at state 2 after increase of the temperature. U1, internal energy of the aluminum rod, or a specific uh, internal energy of aluminum at state 1 before when temperature is 20 degrees Celsius. And if you remember, we this equation U2 minus U1 was equal to C times T2 minus T1. Then if we substitute this one, let me just raise this. Then U2 minus U1 equal to C T2 minus T1, if you remember. Now for U2, U1, we substitute this. Then Q in will be equal to MC T2 minus T1. We have T2, we have T1. We need to calculate M, and also we need to find a specific heat. However, it is given here. Specific heat for the aluminum rod is given. So we have C. It is given in terms of kilojoule per kilogram Kelvin. However, as I said, it is identical to kilojoule per kilogram degree Celsius. Uh, these two units are identical for a specific heat. Then the amount of heat transferred to an 8-meter long section of this road, which is heated by a specified temperature, we can determine by this equation. But before that, we need to find M as well for this road. M, as you know, we can use this equation. This is density equal to mass divided by volume. So here we have rho. We we can calculate volume because uh, we know the length of the road, 8 meter, and we also know how much is diameter of that. Diameter is given. Uh, Let me just find diameter is 5 centimeter. So we have diameter, we have its length. Then we can find the volume of the roads, which is pi d square divided by 4 times L. L is 8 meter, d is 5 centimeter or zero point 0.5 meter, and pi just substitute 3.14 divided by L. And also density is given 2,700 kilogram per meter cube. If we substitute all of these variables, we will find this value for mass of the road or 8 meters, the mass of 8 meters of this rod. And as we discussed earlier, what we are going to calculate is the heat transfer to 8 meters of this rod. So Q in MC T2 minus T1. We have M, we have C, we have T to 400 degrees Celsius final temperature, and we have also initial temperature. Then we find the heat transfer to the aluminum rod per 8-meter section. So for each 8-meter section of this rod, 5,680 kilojoule energy is transferred to the rods. And this is for 8-meter section, and also it is for 1 minute. So the rate of heat transfer, in other words, how much of energy is transferred to the rod per second, we simply can divide this amount of heat transfer, which is transferred to the rods during 1 minute. So 5,680 kilojoule per kilojoule, we need to divide it to 1 minute or 60 seconds actually. Then it will be 261 kilojoule per second. In other words, it means 50,000 divided by 60 will give us 261 kilojoule per second is the rate of heat transfer to these rods. This is final answer, and the question also was about this, the rate of heat transfer to the rods. You can see here how much that specific heat is useful properties of the rods as a solid substance to find the required heat transfer to increase the temperature, uh, uh, consumption of energy, and so on. We can find by that specific heat. We could find this answer if we use the rate form of the equation, like what we had here. If in this equation, Q in equal to mct2 minus d1, we write Q dot m dot, in other words, rate form or uh, the amount per time for mass or heat transfer, we could we could write like this: Q dot in equal to m dot c T2 minus T1. To find m dot, we can write m dot equal to rho v dot. Rho v dot is v divided by delta t. We can calculate like before. Just here we divided by delta t, which is delta t here is for 1 minute, or 8 minutes here. The process is 8 minutes. We just substitute it here, and we will find m dot as the rate form of the mass or mass flow rate. Then q dot in also can be calculated by this m dot. The result is same like before, and q dot in will be 50,680 kilojoule per minute, or 261 kilojoule per second. Same result if we use this method as well. So by this example, we reach end of this chapter. I hope you have already seen all of the video lecture for previous session as well. And let me just briefly review what we have learned in this chapter. We started with moving boundary work for closed system. I introduced you closed system, and I told you how we can find WB or boundary work for isothermal process, constant pressure process, and a polytropic process as well. Then we went further, and I introduced you the energy balance, and we learned how to use that energy balance concept and the general equation to find the different properties for different uh, processes. And also I introduced you a specific heat, or C, for gases as CP and CV, or constant pressure specific heat or constant volume specific heat. Then we also introduce specific heat for uh, incompressible substances like liquid and solids. And finally, we use all of these concepts to find different thermodynamics properties for different substances and different processes. By this, we reach end of this chapter, and which was for uh, closed system. In next session, we will start to discuss about control volume or open system. Thank you very much for watching the video lecture.